Hello, everybody. Teacher Nick here. Just like in life, we have normal people, we got heroes, and then we got superheroes. Today, we are not just going to be talking about a hexagon or a regular hexagon. We're going to be talking about a super hexagon. That's what we're going to be looking at here today. Now, before we even get started, a hexagon is a polygon or a shape which has 6 sides, right? So I'm going to try and draw a hexagon, and then we're going to move to my favorite canvas, and then I show you just how powerful this shape is and how useful it can be, especially when you're doing trigonometry. All right. So what you're going to see here today is probably going to blow your mind if you've never seen it before. There's so much that you can get from a hexagon. All right. So let's get started. So firstly, I'm just gonna put a grid up for accuracy's sake. I don't need you. I don't need you. I don't need you. Take that out. I don't need that point. I don't need that point. I don't need the axis. So hide those objects. Thank you very much. I need this line. So I'm gonna go. So that's one. Gonna do a very straight line, maybe up to there. That's fine. Then I'm drawing a hexagon now, by the way. So I put a grid up so that I can be as accurate as possible. So I'm going to go 0, 1, 2, 3, 4. Let me maybe go 5. And then go 3 this way. How's that? So same thing applies here. To draw this one, I'm going to have to go from there. 0, 1, 2, 3, 4, 5. All right, and then I'm just gonna go straight. That's perfect. Something applies. 0, 1, 2, 3, 4, 5. Then I go 0, 1, 2, 3. Is that missing? 0, 1, 2, 3. So from here, I'm gonna go 0, 1, 2, 3. So right there is fine. And then I'm just gonna join that up. All right. I think I'm gonna like it gray, so I'm gonna gray this thing out right quick. So I'm just gonna I like colorful stuff. So hexagon interior. So that's what we got. So if it's gray, perfect for me. Then what I'm gonna do next, I'm gonna draw the diagonals. So this one goes there. This one goes there. And the last one, this one goes there. That is our super hexagon, and I want to place a point there. Okay, place a point right there in the middle. Oh, maybe I shouldn't. Let me just leave it. I don't need to write a point there anyway. Last thing I'm going to do, I'm just going to hide these vertices. I don't want to see those dots there. I just want the vertices to be sharp. So I'm going to hide those. Okay. So from this, not only should you take away the concepts I'm going to be discussing, but how to use Geometry Sketchpad as well. So I have my perfect hexagon here. So what I'm going to do next, I'm just simply going to hide the grid. I don't need it anymore. So there's my hexagon, and then I'm going to use this program called the snapping tool. So here we go. Snapping tool, basically I just take a snapshot of whatever I want. So here I just want what I just drew, and I need this. Here we go. And then I'm going to go to Microsoft Whiteboard, and then I'm going to paste my guy here. So here we go. So from this hexagon, there's so much that you're going to do. Okay, so there are so many formulae that you can memorize using a hexagon. So that's why I'm using a hexagon today. All right. In fact, I'm gonna go back to Geometry Sketchpad to label. So right now I'm just gonna do a rough sketch here, but to make it super snazzy, I'm gonna go back to Sketchpad and then label it quite nicely. Okay. So one of the trig functions that we're going to use, that we're going to start with, in fact, is tan theta. Okay, and I think that's something that you already know. So tan theta is equal to sine theta all over cos theta. All right, this is what we know. We're going to use this to label this hexagon. All right, and then once we've done that, we're going to go to Sketchpad and put all of this nicely so that it looks super snazzy. All right, so this is how you're going to label this hexagon. You're going to start here. So this would be the first point where you're going to start, and then you're going to go all the way around. You're going to go there, going to go there, going to go there, going to go there, going to go there. So this is going to be the last point. So the first thing that you're going to write is the first thing that you read when you read this trig function. So this trig equation. So if I read this, I don't start by saying sine theta now, do I? But I say tan theta. So that means that's going to be the first thing I'm going to write, because when I read it, that's the first thing I read. So I'm going to have tan theta right here. What do I read next? So it's tan theta is equal to sine theta over. So the second thing would be sine theta. So I'm going to go, second thing there is sine theta. And then the third thing obviously is going to be cos theta. I hope you can see that I chose to use the tan theta ratio because it contains all the three ratios that you want: the tan, the sine, and the cosine. Okay. Now that we have these, we can think about now the reciprocals, now the opposite. So if you are looking for an opposite of tan theta, which part would be opposite tan theta here? It would be right across over there. So that's where I'm going to put cot. If you're looking at sine, which side will be opposite to sine theta there? It would be that one. So that one would be cosec theta. All right? And then obviously that one is going to be this, is that one's going to be sec. Okay. Very important. Place the number 1 right in the middle over there. You want to see how this come in handy as we continue with this. But important to notice, just so when you draw this, you remember, if you're looking at this, if we're to draw a line there, a dotted line there, you will notice that all the trig ratios that start with C are on the right hand side, and then we have the rest on the left. We have cos theta, cot theta, cosec theta. So all those should be on the right hand side, and the diagram forces you to put them on the right hand side. So I'm just sharing this so that you know whether you've drawn your diagram correctly or not. But you start with 10, and then you move and say tan theta is equal to sine theta over cos theta. So the first one that you call is a subject of the formula. The next one that you call is the numerator. The third one that you call is a denominator. Do you see that? This essentially means tan theta would be the subject of the formula because I'm calling it first. If I'm saying I'm starting here, so that means tan theta is equal to sine theta over cos theta. Let's say I was starting here. This would mean cos theta would be the subject of the formula. So cos theta is equal to cot theta divided by cosec theta. Okay, we're going to prove that. For now, I'm just going to go back quickly to Sketchpad and put these labels on there and then come back. Then we do the proof for that. All right. So I'm going to just switch over quickly. So here we are. So all I want to do here, now that you've seen, I want to put the label there that we have. I hope we do have the symbol. So it's 10. In fact, I prefer writing it in small letters, not capital letters. Let's see. Do we have theta there? Oh, what are we going to use? What are we going to use? What are we going to use? Let me see. What do we have here? Okay, we do have theta. We do have alpha. We do have beta. Oh, we got it. We got a lot. All of these are here. All of these are here. So I'm going with theta for now. So I'm going to just copy the theta part. So here we got tan theta, and then we got, okay, I'm going to copy it to sine. This one I'm going to write in caps, sine theta, no, sorry, small caps. So this one's going to be sine theta. And then this one is going to be cos theta. Oh my word. cos theta, and then opposite to tan. Who is the opposite of tan? It's going to be cot theta. We are on this line. This one is taking to sine, so who's the opposite of sine? Cosec theta. And then last but certainly not least, who's the opposite of cos, or the reciprocal of cos? This one is going to be sec. Okay, so I'm just going to rearrange this nicely. So you over there, you come a little bit closer. Yes, come closer over there. And you come over here. You get closer. Don't be shy. Don't be shy. The hexagon won't bite. Don't be shy. Here we go. Here we go. We got it. Okay, so now I'm going to snap this. I'm going to snap that. So let's take a snapshot of this and take it all the way back. It looks quite neat. I'm proud of myself. Believe that. All right. So I don't want anything here right now. So what I'm going to do, I'm going to just undo, take everything off, including you. Okay, I can just delete you, really. And then just paste. Here is my super snazzy hexagon with all the labels. You know how it is. Okay, so let's keep it over here. And please don't forget your host. You are being hosted by Teacher Nick. Who else could it be? So now that we have our hexagon here, the one thing that is missing now is that 1 in the middle. Doesn't look that good, but guys, it's a 1. Please stop judging me. I'm trying here. Okay, let me try again. Let me give it another shot. That's a 1 in the middle. As far as I'm concerned, that's a 1. You don't see it, you need to get a pair like me. Anyway, so you remember how we started. We started by saying tan theta is equal to sine theta over cos theta. And if you look at our diagram, the one that you call first is the subject of the formula. It's going to be alone on the left-hand side. The next one that you call is going to be the numerator. It's going to be the top part of the fraction. And the third one that you call is going to be the denominator. You know this trig ratio, right? Now, let's have a look at another trig ratio here. Let's say for interest's sake, I wish I was doing this live. Let's say for interest's sake, you say, I want to start at cos. So if you start here, it means cos theta is going to be the subject of the formula. So that means you're going to have cos theta equal to, doesn't look like a theta, doesn't matter. We're not artists here. So that means that will be equal to cot theta all over sec, cosec theta. This is the third one, cosec theta. And we can actually prove this, okay? So the left-hand side is equal to cos theta, and the right-hand side is where we're going to be working the most. The left-hand side is sorted, and the right-hand side is equal to cot theta all over cosec theta. All right? But we know, according to this, we know that cot theta is the inverse or the opposite of tan theta. So if tan theta is sine theta over cos theta, then it means cot will be the opposite of that. It will be cos theta over sine theta. So let's write that. In fact, maybe even before we write that, we can go and say, let me just put this back like so. Maybe even before we say that, we can rewrite this and put the division sign on there. So in other words, we can say this is cot theta divided by cosec theta. All right, I'm not going to prove all of these. You can prove them at your own time. So we know that cot is the inverse of tan theta. So that means this would now mean this is cos theta over sine theta, because tan is sine theta over cos theta. So this is what this will be. In fact, if you are to read this, you're going to have to read it in an anti-clockwise direction and you get the same thing. So if I start from cot and I go back this way, cot would be equal to cos theta over sine theta. So when you go clockwise, everything you're going to get is still correct. You go anti-clockwise, everything you get is going to still be correct. So this will be divided by, and then cosec, if you look at the diagram that we have here, it is actually the opposite of sine theta. So if sine is sine over 1, that means cosec is 1 over sine. So that means here we have 1 over sine theta. It is the reciprocal of sine. Sine theta. All right. Now from primary, we've been told that if we have two fractions being divided with each other, and you want to change the division sign, one of the fractions, the one on the right, will need to change. Whatever is the numerator becomes the denominator, and whatever the denominator becomes the numerator. So in this case, I want to change this division sign into a multiplication sign. So the fraction on the right will flip over. So that means here we're going to have cos theta all over sine theta. I'm not going to change anything there. Times, then this is not going to be sine theta all over 1, right? And I'm sure you can notice that we have stuff that is going to cancel out. So here, sine will divide the sine that we have over there. So that means we're left with cosine, we're left with cos theta divided by 1. And cos theta divided by 1 is cos theta. So I'm going to put this up. Oh, sorry. So if this cancels out, I'm left with, I need to use the black. I'm left with cos theta divided by 1, which is the same as just cos. Anything divided by 1 remains the same. So I'm left with cos theta, which is also the same as the left-hand side, if you remember from when we started. If you remember, when we started, the left-hand side was cos theta from the original equation. Make this even smaller. So we had cos theta is equal to cot over cosec theta. So you can do this proof for all of these trig ratios and it's going to work. So if you need a way to memorize a lot of these trig ratios, just draw your hexagon and put that one in the middle. Start with tan, right where on the equator level or at the center. Tan, sine, cos, and then you write the opposite of these trig ratios. Then you're good to go. So here I was just proving that it is true that if I were to go clockwise, if I start here and say cos, it would mean cos is equal to cot over cosec. And here it is shown that cot over cosec is actually equal to cos theta, which is equal to the left-hand side. So I'm not going to be proving each and every trig ratio that we have here. I was just showing you this so that you know what to do. All right? I hope you're good with this. Now, we're not even closer to being halfway. There's so much that you're going to discover that you can actually memorize just by drawing this hexagon. Then we call it a super hexagon. All right? So just chew on this, and then we're going to get into the next session right about now. You can pause the video, have a look at what I've just done, and then if you have any questions, you're going to drop the questions in the comments, and I'll be happy to respond to you. All right? So let's go to the second part now. Okay. Now that I've cleared everything on the screen, I'm just going to remind you what we did. So with this hexagon, you can memorize your trig functions. Okay? So the first function that you call, or the starting point, is the subject of the formula. The second one, denominator. The third one, numerator. I'm not going to write all of them. But since we have 6 trig ratios here, it means if you go in a clockwise direction, you can get 6 trig equations. If you go in an anti-clockwise direction, you'll also get 6 trig equations. In other words, if I were to start from here, so from here, this is the first one we did. We said, let me put a pen on. We said tan, sine, cos. So that means tan is equal to sine over cos. And then let me undo that. And then if you start here, it means the sine is equal to cos over cot. If you continue, it means, if you start here, it means cot is equal to cosec over sec. If you decide to go the anti-clockwise direction, if you say cot would be equal to cos over sine. If you go to sine, if you start here, sine would be equal to tan over sec, and so on. All right. The first one is the subject of the formula. The second one is the numerator. The third one is the denominator. All right. Now we're going to be looking at what we call identities. In mathematics, an identity. Now everything that we did before is coming back. I think it's Control Y. Perfect. Sorry about that. So we have something called an identity or identities in mathematics, and I don't think people quite understand the difference between a normal equation and an identity. So when we are dealing with equations, there are equations where you can substitute any value in the variable and the answer will always be the same, meaning the left-hand side will always be equal to the right-hand side. Let's make an example. An equation like 2x equal to x plus x. This type of equation is an equation we call an identity. In other words, whatever value of x you choose, the left-hand side will always be equal to the right-hand side. So if I decide to say, well, I want x to be 10, so that means this would be 2 into 10 equal to 10 plus 10. I think you can catch my drift. 2 times 10 is 20, equal to 10 plus 10, which is also 20. This is what makes an identity an identity. This will always be the same. This will always be identified by the same pattern. All right? But we do have equations, but an identity is an equation, but a special kind of an equation. We do have equations that are not identities. So not all identities, not all equations are identities, but all identities are equations. Very important to note. So an example of an equation that is not an identity is some like, normally it's characterized by having one variable on the side. So if I have 4x equal to 12. Here, there's only one value that will always make the left-hand side equal to the right-hand side. What number must I multiply 4 with in order to get 12? That would be 3. That is literally the only number I can put there. But if you compare something like 2x equal to x plus x. In the previous example, I used 10. Here, I can use another number. Let's say I'm using a number 3. So 2 into 3 will be equal to 3 plus 3. 2 times 3, 6. 3 times 3 plus 3, 6. So the left-hand side will always be equal to the right-hand side. Doesn't matter which value of x you choose. But with this one, there's only one value that will make this statement true. As soon as I use a number bigger than 3, the left-hand side and the right-hand side will not be the same. I use a number less than 3, the left-hand side and the right-hand side will not be equal. So here, the only solution is to put 3, which will be equal to 12. So 4 times 3 is 12, which will be equal to 12. All right? So this is not an identity. This is the identity. So in trigonometry as well, we have identities, and we're going to use this now to determine or to memorize these identities. Now, we do need that one here. That's a perfect one. You can judge me if you want, but I think I nailed it. All right, so I'm going to just take these off. Okay, that's good. Now, all you have to do is to think about multiplying the opposite trig ratios. So what do I mean by this? If I take this trig ratio, I have a wrap on in my hand. So if I take this trig ratio and I multiply with this trig ratio, they are going to give me 1. In other words, sine theta times cosec theta will give me 1. This applies throughout. I take cos theta multiplied by sec theta, I'm going to get 1. I take tan theta multiplied by cot theta, I'm going to get the 1. Let's see. Let's take sine theta times cosec theta. So we're looking at these two. So if I say sine theta times cosec theta, what does this equal? Okay, so we're going to simplify this. So we have sine theta times cosec theta has a relationship with sine. So in trigonometry, we're always making these relationships. So since I have sine here, I would want to convert the cosec in such a way that there is a sine in it. So what is it then? Cosec is actually a reciprocal of sine theta, which means it is 1 over sine theta. Any number, any variable has a denominator of 1. If the denominator is not stated, it means it has a denominator of 1. So let's do the multiplication now. We can just simply cancel out, but we're just trying to drag this out anyway. So it's going to be sine theta times 1, which gives me sine theta divided by, and then I go and say 1 times sine theta, with anything multiplied by 1 remains the same. So sine theta. If you remember the previous video that I made, we said any number divided by the same number will always be equal to 1, as long as the number being divided by is not equal to 0. So this means if you take sine theta and you are dividing with sine theta, then we should get 1. So this is equal to 1. We can prove this. We can take a calculator and choose, because we can take a calculator and choose the value of theta there. Okay? We can choose any value we want. All right, let me take the calculator on. I'm going to put this on. So let's say we have sine, what, 56. Just going to try and be as random as I can. So if you divide this by sine 56 again, I mean, you're always going to get 1. All right? So remember that. So I'm not going to prove for all these, but the opposite trig ratios, when you multiply them, they give you 1. So, right? So you can really try out all the trig ratios here. It's entirely up to you, but that is the case. In fact, if you were to take this and punch in on your calculator, you'll see that it's actually indeed equal to 1. All right? So now we're going to move on to another section. There's so much that you can really store here in this hexagon. There's so much information that is on here, and yet we are almost halfway through. All right, so if I were to take cos theta multiplied by sec theta, that means that should be equal to 1. So that is the identity. So in this case, this is the identity. All right, sine theta times cosec theta will always give me 1. Whatever I choose, whichever value I choose, should always be giving me 1 right there. All right. All right, so what I'll do now, I'll take everything that's on the board here. I erase everything now. I want us to do more trig equations from this diagram, from this beautiful diagram, this super hexagon. All right, so I'm going to bring back the 1 in the middle. Now, what we're going to do, we're going to choose any trig ratios. The ones on the ends, if you multiply them, they give you 1 in the middle. Not my head. So in other words, if I just choose, I say 1, 2, 3. Tan theta and cos theta are on the ends, sine theta is in the middle. It means if I multiply those two if I multiply this one and that one, they are going to give me this one as an answer. You can choose any three. The ones on the side, when you multiply them, they give you the one in the middle. So let's try this right now. So I'm saying to you, if you take tan theta multiplied by cos theta, you will get the answer which is right here in the middle. Well, when we mark, we use the tick. You will get that answer in the middle, which is true. So in this case, it means tan theta, we know that tan theta is actually sine theta all over cos theta times cos theta. Obviously, you can just say these are going to cancel out, or you can drag it out if you want and say there's one there. Sine theta times cos theta, this will be sine theta cos theta all over cos theta times 1 will remain the same, so this is cos theta. And then cos theta will divide cos theta. Look at that. What are you left with? You are left with sine theta. So when you check tan theta, multiply with cos theta, that's what you're going to get. Let's check another one. Check another one. Let's say, let's take 1, 2, 3. This means tan theta, okay, you don't always have to multiply with 10. So to ensure that I don't create that sort of thinking, but it's either going to have 10 or going to have cot if you want to have 3, so it doesn't matter. So 1, 2, 3. So if you take those 3, it means if I take this one and I multiply with that one, the answer should be this one. Or if I decide, Control Y. If I take this one, and that one, it means the ones on the end, it means this one times that one will give me cot. Let's try it out. So I'm gonna go blue. Let me go green. So that means if I take cos theta times cosec theta, the answer I'm gonna end up with is going to be cot theta. That's what I'm told. So let's see if that is indeed the case. So cos theta is just cos theta. So cos theta is cos theta. But cosec is the opposite of sine, meaning it's a reciprocal of sine, which means it is equal to 1 over sine. So this is multiplied by 1 over sine theta. If you have cosec, you always take it back to 1 over sine. You have sec, it's 1 over cos, you know. And then look at this now. From here, we know that we have a 1 there. So cos theta times 1 is going to be cos theta over 1 times sine theta is going to be sine theta. But cos theta over sine theta is the opposite of sine theta over cos theta, which was 10. So cos theta over sine theta is actually equal to cot theta. So now you know 10 and cos would give you that one. These 2 will give you that one. These 2 will give you that one. Right? And these 2 will give you that one. You can go clockwise, you can also go anti-clockwise. 1, 2, 3, the 2 on the sides, the two trig ratios on the sides, they are actually equal to the one in the middle if you multiply them. So tan theta times cos theta multiplied by each other, they are going to give you sine theta. Cos theta times cosec theta will give you cot theta. Sec theta times cot theta will give you cosec theta. All right, so that's what it is. And that is still the tip of the iceberg. I'm kidding, we're about to finish now. All right, so let me clear the screen now. Do you remember complementary angles? Yes. So we can use this diagram again to memorize complementary angles. So a complement of an angle is like the opposite of an angle. All right? So notice that we have 3 horizontal lines. That's all we're going to use to show all the complementary angles that we have. All right? So if you look at this line, so if you look at this line is telling us that sine theta is equal to the complement of cos. Remember, when you talk about a complement, we're talking about an angle that is 90 degrees minus theta. And we know this to be true. And same thing applies here. Maybe even before we do the second one, how about we prove with the first one? Remember, a complement of sine theta would be cos 90 minus theta. So in other words, this will change and be sine theta. So cos 90 minus theta is the same as sine theta. All right. So let's check this out. If we're to put, let's choose an angle there. Let's say an angle we're choosing is we're choosing theta to be 60. So whether it's 60, whether it's theta, we put 60. So if you do sine 60, you need to remember your triangle now. This will give you root 3 over 2. And this is equal to this thing. So if you say cos 90 minus theta, but we chose theta to be 60, so basically this is cos 30. Oh, sorry, 60. What does it give you? Root 3 over 2. All right, so this can also be proven using the triangles, the rectangle triangles that we used back in the days to find special angles. Let me quickly draw that one here so we can see. Let's say we are choosing 60 as our angle, so as our theta. So that means we are saying here sine theta is equal to cos 90 minus, and we chose theta to be 60, so I'm putting 60 there. I don't know why I put theta back here. It should be 60. This is what you're saying basically. This is an identity as well. You can choose any angle that you want. But we are saying sine theta or sine 60, for instance, you could have chosen any number to put there. You could have chosen 40 or whatever. So I'm saying sine 60 is equal to cos 90 minus, it's cos 90 minus 60. Let's prove that. If you remember this diagram that we had, that we're using back in the days, we had some like, here we have 90 degrees, and then we'll have 60 degrees, here we'll have 1, and then here we have 30 degrees. Obviously the total must be 180, and then here you're going to have root 3, and then here the hypotenuse is going to be 2. Now remember, sine theta is actually what? Opposite over hypotenuse. So sine theta is opposite over hypotenuse. In this case, we are looking at sine 60. There is sine 60. Sine is equal to opposite. Sine theta is equal to opposite over hypotenuse. Right. If you look at angle 60 is opposite which side? That side. So that side is square root of 3 over. Hypotenuse is 2. There you have it. So sine theta is equal to that. And if you were to simplify this side, the right-hand side, cos of 90 minus 60 will actually end up being, let me remove this, will actually end up being cos 30. I don't need a bracket in fact, but it's fine. Will actually end up being cos 30. And if you check cos 30 on the diagram, because we said 90 minus 60, cos 30 on the diagram, there is 30. Cos, the trig ratio of cos theta is equal to adjacent over hypotenuse. So adjacent means next to. So if you look at cos 30, adjacent is square root of 3 all over hypotenuse is 2. As you can see, The right hand side is giving us square root of 2 over 3, and the left hand side is also giving us square root of 3 over 2. So these two are actually equal to one another. So what else can you say from the diagram? You can see that if you go the opposite directions, it means, for instance, for cot, this will mean cot theta is equal to the complement of tan theta. So it's going to be tan 90 degrees minus theta. Okay? That's what we're going to get. Same thing applies. Cosec is equal to a complement of sec, or second. All right? And now we're going to do the last part, then I swear I'm going to let you go. All right? So now we're going to look at the last identities. So I'm just going to clear everything. I'm going to clear the canvas. It's going to take away even the headings, but doesn't matter. I'm going to clear the canvas. So the canvas is going to be empty now. I'm going to go back here. There are a few triangles that I want to highlight that are important, that are going to give us our last identities. All right. So I want to start this one. Sorry. I'm going to move this here. So this one, that one, and that point. I want a different color there. So triangle interior, yes. So, okay, I'm going to undo a lot of this. Okay, I can't do this. So I'm gonna have to do everything. Excuse me. Alright. So I want you to focus. Okay, I can go here. I want you to focus on that triangle. I'm going to choose a different color for it. Let's make it red. And I also want you to focus on this triangle. Okay, sorry, I'm going to move this down. I need you to focus on this triangle. Don't worry about the others. Okay? Why are you selecting? Okay, so I want you to focus on that triangle. And obviously the last one is, move this guy over. This is the last triangle I also want you to focus on. Okay, I want you to focus on these three triangles here. We are creating our last identities. And like I said, we need to have one somewhere. I'm going to write the number 1. And I didn't know I didn't do this from the get-go. All right, so the number 1 is going to go right there. All right, now that is super snazzy over there. Then I'm going to take a snapshot of this. Take a snapshot of this, and let's go back to whiteboard. Okay, so at hand I have a rubber. I don't know why. So the last identities are the square identities that we're gonna be dealing with here. We're gonna go clockwise, and then we're gonna go anti-clockwise. Okay. So in every triangle, you choose your starting point. Okay. So we look at these as if they were squares now. So if I move, the color that will stand out is probably this one. So I'm going clockwise. So I'm gonna write, I'm going like this, clockwise. Even here, I'm gonna go clockwise. Even here, I'm gonna go clockwise. Okay? So what does it mean? I'm gonna say sine square theta plus cos square theta will be equal to 1. So you go there. I'm going clockwise. So that one. So the identity that we have here will be sine square theta plus cos square theta is equal to 1. Let's look at another one. Look at how I'm going to move now. Like I said, you're going clockwise. So if I start from, let's say 1, because 1 is a square as well. So 1 squared plus cot squared should give me the third one, which is cosec squared. In other words, 1 plus cot squared theta should be equal to cosec squared theta. I'm going to use a different color. If I go 1, 2, 3, so then it means I started at tan theta, right? So that means tan theta plus 1 will be equal to sec theta, sec squared theta. So tan squared theta plus 1 is equal to sec squared theta. And my squared are horrible. So let me put that there. Perfect. Alright, if you choose to go the anti-clockwise direction, the same thing is going to happen. Remember, you're focusing on the 3 red triangles here. Okay? So let me erase some of this. And we go the opposite direction. So now we are going to go the opposite direction. All right? So in other words, this is how we're moving now. Okay, that's the direction now, anti-clockwise. Okay, let's make the first example. That means, remember at the beginning we said 1, 2, 3. Now we're going back. We're doing the inverse now. The only difference here is that now we're going to be using minus, the opposite of plus. So if I take this one, that one, and that one, this means 1 minus cos theta is equal to sin theta. I keep forgetting the square. So 1 minus cos squared theta is equal to sin squared theta. Let's do another one. This is a different color. Let's say we're starting here. So it's going to be 1, 2, 3. So what does this mean? This means cosec theta, cosec squared theta minus cot squared theta is equal to 1. Let's do the last one. So I'm starting from here, I'm going there, and I'm going there. So this means this is how I'm moving here. So this means sec squared theta minus 1 will be equal to tan squared theta. From one diagram, look at how many formulae that we've been able to extract. Hence now you can see that this is a super hexagon. Alright, it's not a normal hexagon. There's so much that we were able to extract from here. So if you know the basic structure that you need to draw and you know the directions that you need to move, then you will be on your way to remembering all the identities and the trig ratios that you need in order to solve any trig problem. Alright? Ladies and gentlemen, I'm going to stop here. I tried to make this video as short as possible, but there was so much to share. If you liked the video, if you learned anything, just give the video a thumbs up and share the video far and wide. Much appreciated. I'm out.